The last video we spoke about the different characteristics of sound, and we primarily started with the absolute characteristics of sound, which was amplitude, wavelength, frequency, and time period. And then we also explored the subjective characteristics of sound, which was pitch, loudness, timbre, note, noise, and tone. All these subjective characteristics are primarily our ear's response to the actual absolute characteristics, right? So which means that this can change from person to person. And there was one other characteristic which we'll explore, which is the idea of intensity. So sound intensity is also an absolute characteristic of sound, and we equate sound intensity to the sound energy per unit area. Sound energy per unit area. So sound intensity is very similar to the idea of pressure that we explored in one of the earlier chapters, where we equated pressure to thrust by thrust per unit area. The thrust was nothing but the force that was perpendicular to the surface, that was thrust, and the thrust per unit area is what we termed as pressure. So just to recap, pressure was thrust per unit area. Yeah. So similar idea in the context of sound is sound intensity, and sound intensity is related to loudness. Both are not the same. Primarily, when the intensity is very high, we say that it is loud, and when the intensity is low, we say that it's not loud. And loudness, as you know, that is more of a loudness is not an absolute characteristic. It is a subjective characteristic, right? But intensity is an absolute characteristic. It's going to remain the same irrespective of who perceives that sound. So let's quickly recap one other aspect of sound, which was about the need for a medium for sound to propagate. We did explore, and we also went through an experiment where a medium was crucial for us to hear, for us to hear or perceive sound. For that, the sound will have to propagate, and if the medium is completely empty, without air particles or solid or gas or liquid particles, then it means the sound wouldn't propagate and we wouldn't hear. And we saw that through that example of a jar, an electric bell that we place inside a jar, and when we suck out all the air, we see that we can experiment and see that the sound will turn feeble, and at one point in time you'll not be able to hear anything while the bell is still ringing inside the jar. Right. So medium is key, and sound typically travels faster in solids when compared to liquids. Solids when compared to liquids, when compared to gases. So speed of the sound is fastest on a solid. Sound is fastest. The second fastest, sound is fastest on the solid when compared to liquid, and sound is faster on a liquid when compared to the gases. And also, as the temperature increases, temperature of the medium increases, the speed of sound would also increase. So, for instance, in air that is for 0 degrees Celsius, the speed of in air that is when the temperature is 0 degrees Celsius, the speed of the sound is approximately 331 meters per second. But in the same air, but at 22 degrees Celsius, the speed of the sound becomes 344 meters per second. So this is the speed of sound in air based on the temperature. So sound, when the medium is solid, the sound is the fastest, and when the medium is liquid, it is slower than solid, but it is still faster than gas. And when the temperature is going to also influence the speed of the sound wave, and as the temperature increases, the speed of the sound wave also increases. Now, if you observe, the speed is not a huge speed. As you'll soon learn the speed of light, which is way more than the speed of sound. Light travels at light is extremely fast, whereas sound wave is not. And this is one of the reasons why when there is a thunder, or a lightning, you basically hear the thunder. When there is a lightning, you hear the thunder first. You see the lightning first before you hear the thunder. That's because light travels faster than sound. That's why you see the lightning first and then hear the thunder later, right? So the speed is not too high, and there are objects which can be made to move at a higher speed than this. And whenever an object travels at a speed greater than the speed of sound, we call those objects as we call that speed as a supersonic speed. So supersonic speed. Supersonic speed refers to the speed of objects when that travels at a speed that is greater than the speed of sound. So typically, some of the jets, fighter jets, and all that, they tend to move at a much higher speed than this, for what you see here. And we say that those objects are traveling at a supersonic speed. And when an object moves at that high speed, that is at a speed that is greater than the speed of sound, when an object moves at a supersonic speed, they do create a sound. It's a sharp sound. I mean, you can observe in fighter jets that fly on the sky. I mean, those fighter jets that move at a supersonic speed, they create a sound, not just because of that sheer speed. And that sharp sound that is created by those fighter jets is primarily because of the pressure variations that they are creating around that, right? The vibrations of that object, the vibrations of the air particles around that is what is the cause for that sharp sound, and that's called sonic boom. So sonic boom is the sharp sound that is created by pressure variations of objects that are moving at a supersonic speed. So with this, I think we have pretty much covered all the characteristics of sound, and we will now talk about another important property of sound, which is reflection. So reflection, using a different color. So sound bounces off. Sound bounces off some of objects, be it liquid or solid. Just like light, the way light reflects on a glass pane or on any other surface, sound also bounces off, or it reflects, and it has a very similar behavior as compared to light. And you can see that when sound reflects back and it reaches you when you speak, and then let's say when somebody speaks, and that sound wave hits a particular surface and then it comes back, and which means that and if the time that is taken is more than 0.1 seconds, you would hear the voice again. You would hear your own voice again, and that's what we call as echo, right? So echo is caused by reflection of sound, and you can recognize echo only when the distance, only when the time between the moment you originally spoke and the time by the time it came back to you after reflection is more than 0.1 second. And only when the time taken is 0.1 seconds by the time it reflected and came back, you would hear the voice again, and you'd be able to perceive the echo. If the time taken by reflection is less than 0.1 seconds, that brain will not be able to identify that, so you wouldn't even know that it has reflected. So when the time taken by the sound is more than 1 second, by the time it gets reflected off, it gets bounced off from a surface. Your brain will be able to recognize that difference, and that's when we can realize that echo. So this typically a sound sound reflects when the sound hits an object, hits a surface, and then it reflects, and we call that as it's very similar to light. So it reflects at the same angle at which it hits the surface. So if you consider this angle, if you consider this to be the perpendicular line drawn to the surface, and the angle in which it hits the surface is the same angle with which it will bounce off the surface. So this angle, the angle at which the sound wave hits the surface is the same angle by which it bounces off the surface. So these two angles are the same. So in a sense, this angle with which it hits the surface is what is called as angle of incidence. And this angle is called angle of reflection. And both the angles are the same for sound wave. So yeah, so that's the idea of reflection, and there are different uses of reflection, and which reflection of sound. We can carefully manipulate this reflection of sound for our advantage. And so one possible scenario is when in a theater or in a concert hall, you might typically observe that the roof of the concert hall or the auditorium is typically curved, and that the whole idea of that is to maximize reflection, so that all the sound that hits the surface reaches all the corners of the hall, right? So everybody should be able to hear it, and that's why they typically keep it curved. And there is also a chance that too much of reflection of the sound is also not going to be pleasant, because the sound, imagine a concert hall or something where the sound hits the ceiling, comes to the bottom, and then it hits the surface, and then it once again bounces off. What will happen is you will end up hearing the same sound over and over, and that echo, that recursive echo, or that repeated echo, is what is called as reverberation. So when you observe that sound is reflected in that closed surface, and that you keep hearing back the same thing again and again, we see that that the phenomenon is called reverberation. And reverberation is also caused because of the reflection of sound. It's a recurring echo, and that is also not pleasant. So the idea is to reduce the reverberation, and some of the common approaches to reduce reverberation is to use some special absorbents of sound. So there are some materials which absorb sound, but they don't reflect sound, like fiber board and all that. So typically they will cover the seats of an auditorium and some parts of the auditorium with those sound absorbents, primarily to reduce reverberation, so that the sound is not constantly reflected, and it is you keep hearing the same thing over and over, but rather it gets reflected once on the ceiling, and then it possibly gets absorbed by the absorbents that are placed on the other parts, primarily to reduce reverberation. So primary use of reflection, there are some nice use of reflection, practical uses of reflection. One, something that we just saw, which was the curved cinema hall. The other possible examples are you can see the idea of a megaphone or a loudspeaker So typically, a megaphone or a loudspeaker is somewhat like this, right? Where you can, you can, whatever you speak, whatever you speak, whatever you speak through that megaphone is basically, you ensure that it is sent, the sound is transmitted, or the sound is propagated in a uniform direction, and which means that you're through the small hole, the sound is reflected, and it ensures that all what you speak goes through the small hole, and it goes, it is all directed in one single distance, instead of the sound getting lost in all possible directions. All what you speak is passed through the small opening, and internally the sound is reflected, so that it doesn't come out of this medium. And then all what you speak is all the intensity is saved and channelized in one single direction. Same is the case with a stethoscope that is used by a doctor. When a doctor places the stethoscope on your chest, typically the sound is collected, and that through the stethoscope tube, the sound is held. It is not allowed to get out. Rather, it is reflected, and it is held inside that stethoscope for the doctor to completely hear the vibration of the heart. Right. So these are all some good uses of the reflection of the properties of the sound, which is reflection. Right. You can make by carefully reflecting the sound within a surface, you can channelize the sound in a certain direction, just like how you channelize a sound using a megaphone, and just like how you channelize that sound through a stethoscope. The last aspect that we'll talk about is sound that is audible. So we all hear certain sounds, and we cannot hear, as humans, we don't hear all possible sounds. And animals are more sensitive, and they can hear certain sounds which we don't hear. And typically, children's ears are more sensitive than grown-ups, so they can also hear certain sounds which grown-ups cannot hear. And so there is a range. So there is a certain range which can be sensed and perceived by the human ear, and that range is typically the hearing range for humans is typically 20 hertz to 20,000 hertz. So this is the audible range. This is the audible range or the audible frequency range. And it is the sound that has a frequency of this is all what is going to be heard by humans. So the audible frequency is primarily 20 hertz to 20,000 hertz. I think there is a delay. Yeah, it's back here. So 20 hertz to 20,000 hertz is the audible range. And anything that is less than this, anything that is less than 20 hertz, we call it infrasound or infrasonic sound. And anything that is greater than 20 kilohertz is what we call as ultrasonic sound or ultrasound, right? So that's an important property of sound. So this is the audible range, 20 hertz to 20,000 hertz, and anything less than 20 hertz we cannot hear, and that's called the infrasonic sound, and anything greater than 20 kilohertz is what we call as ultrasonic sound, and that's something that we don't hear. At this point, it might be helpful to understand the working of a hearing aid. For some of them, some of them might have that disability of not being able to hear properly, right? So the idea here is the idea of the hearing aid, to help them hear what we are able to hear. And the core idea of the hearing aid is to raise the frequency of the sound, so that they have a better chance of hearing it. And the way the hearing aid works is in 3 steps. So the hearing aid has 3 components to it. So the hearing aid has 3 components. It has a mic component. It has an amplifier. We'll explain what's the use of each of this. And then it has a speaker. So these are the 3 parts of a hearing aid. And the way it works is the sound that reaches their ears is actually first processed by the hearing aid before they get to hear it, right? The person with the hearing disability. So the first step that the hearing aid does is it converts through the mic, it converts the sound waves into electric signals. So that's the purpose of this, to convert sound waves to electric signals. And the second step, the idea of the amplifier is to amplify the electric signal. So basically to raise the strength of the electric signal. So this amplifies the electric signal. And the idea of the speaker is to once again convert that electric signal into a sound wave again, so that the person with the disability can hear it. So through this, this is to convert electric signal to sound waves. So you have raised you have actually raised the frequency of the original sound, and now the person has a better chance of hearing it, and that's the idea of a hearing aid. So I think we'll stop here. There are a couple of more concepts that are still left, and we'll cover that in another video.
One final thing before you leave. If you wish to revise the concepts that you've just learned, please look up and try out the free Revise app bot on Telegram app. Telegram is available for free on both iPhone and Android. Also, if you did like the content that you just watched, please do like, share and subscribe this with your friends. Thank you.